Okay, this is lab 5 of Physics 2212, and in this lab we are going to be observing a magnet falling through a conductive tube of aluminum foil. We're going to observe the results of this in an experiment form, and then we'll also model the interaction computationally and compare the results. So my observed time for the magnet falling through the tube was 1.028 seconds, and my computational time via my GlowScript code was 1.137 seconds. So there's a lot of physics principles that went into this lab. Most notably is Faraday's law. So this states that a change in magnetic flux is going to create an induced EMF on whatever the loop is. So the equation is up there in the top right, and it just states that the induced voltage is going to depend on the number of loops, the change in time, and the change in magnetic flux. We're also going to use Lenz's law, which states that induced electric currents create magnetic fields that oppose the change in flux. And then back to the basics, Newton's third law, we'll just use that to know that the force on the magnet is going to be opposite in direction and equal in magnitude to the force on the loop. The last things are we're going to use the EMF of a moving dipole as well as the magnetic force on a wire in our calculations later on. So the procedure, I constructed a aluminum foil cylinder, which was going to act as the conductor, and then I recorded its length, thickness, and radius, and then dropped a magnet down that aluminum foil cylinder, and I took a video of the process to record the timestamps when it first entered and exited to measure the time it took to fall, and then I repeated that 5 times to get the average of my results. So here are my data and observations. On the left side, you can see that the mass of the magnet was 0.023 kilograms. I used the magnetic dipole moment that I found in lab 3. And then as far as the cylinder goes, the length was 0.3 meters. You can read the width and radiuses there. The middle table is where I recorded all of my trials, and as you can see, the average was 1.028 seconds. For observations, it was pretty clear that the magnet was falling slower when it went through the cylinder than it would have if I just dropped it on the floor. So in terms of this lab, that meant that there was a the downward force had a smaller magnitude, indicating that there was some upward force acting to cancel out the force of gravity, and that was applied by the cylinder. So here's where I modeled it with my code. In block 1, that's just where I set the physical constraints of the experiment, so making sure the length, width, and inner radius was what I actually did in my experiment. That second block had to do with the magnet, so making sure its initial conditions were set correctly. I had the right mass and magnitude of the magnetic dipole moment from lab 3. And then I also used the lines 68 through 71 to make sure that the dipole was set up correctly when I would go to model it. Block 3 is where I created the definitions for the magnetic field of the bar magnet as well as the magnetic flux. So I set these equations using I made these definitions based on the equations of my physics principles slide. And then the benefit of doing it this way is that you can just use these definitions in the for loop to check at various points in time. So I didn't include the for loop in here, but just kind of explaining it. Basically, the for loop checked to see if the magnet was in the tube based on its position, and then it iterated through each ring to find the net magnetic force on the magnet. And then from there, you could find, or the code found the magnet's acceleration and updated the position. And then from there, you can see in block 4, we just visualized that so you could see it in a graph. So that graph is on the right hand side, so you can see the acceleration and then just the constant velocity, and that the total time in the tube was 1.137 seconds. And then on the left, you can just kind of get a picture of the magnet falling through that tube. So the tube was this gray part, and then the blue and the red are the north and south poles of the magnet. So the questions, you can't use a Ferris tube because that obviously contains ions and they interfere with the Faraday's law, so the induced magnet wouldn't work the same way. And then if the resistivity of the conductor was reduced to 0, the current's magnitude would increase, and that's because the current and resistance are inversely proportional. So in other words, the magnet would just fall even slower. And then if there were holes or slots in the cylinder, the magnetic force would not be as strong, so the magnet would fall faster. And that's because if you go back to Faraday's law, you know that the force is influenced by the number of loops. So by reducing the number of loops, the force wouldn't be as strong, and so the magnet would fall faster.